started, please. So we're talking about power series. So remember what power series are. Power series are functions that can be expressed in this sort of form. Sum of a sub n x to the n from n equals 0 to infinity, or it could be something like this, a sub n x minus c to the n from n equals 0 to infinity. Right? This is so-called power series centered at 0. This is a power series centered at c. Right? You see that these things are basically infinite polynomials. Why are they called centered at 0 and centered at c? Well, that has to do with the domain of convergence, right? So we have this theorem about the form of the domain of convergence, right? And it said basically that if your power series was a power series centered in c, then the domain of convergence would be centered at c, right? That the domain of convergence either looked like the point c itself, or it looked like the whole real line, or it could be an interval. It could be an interval, open, closed, or half open, half closed. But that interval would have to be centered at c, right? That was this theorem of the form of the domain of convergence. Okay? And the theorem came from this lemma that said something interesting. The lemma said that, I'll just draw a picture of it. If you're centered at c and you converge at some point x naught, right? If you're centered at c and you converge at some point x naught, then something happens. Does anybody remember what happens? We said it when we were talking about it. We took c to be 0, but it could be any point. So let's say you have some power series. You have some power series centered at c, and you know that you've got convergence at some point x naught. Tamina.
It converges between the x naught, and then if it was 0, you would say negative x naught.
Yeah.
Do that interval.
Yeah. So it will converge in a symmetric interval, right? It will converge in this interval here, absolutely, right? So that was the theorem. Maybe I should post the lemma. Maybe I should write it up instead of just drawing it. Right? So you have some power series given, a power series given a power series centered in c. If it converges at some x naught that's not equal to c, right? So here's a picture. Here is c. You converge at some point x naught, right? Then it converges absolutely. It converges absolutely whoops, I shouldn't see, not, this is just c, sorry. In c minus delta, c plus delta, where delta is this distance, and delta is the distance between c and x naught. And it's this lemma that gives us the theorem. This lemma gives us the theorem. everybody all right with this? At least those words. Right. Okay. So let me just draw a picture here. Suppose you have a power series. Suppose you have a power series, and you know that it converges in this interval r, negative r comma r. Okay. So you know that it converges at this point, right? Right. It converges at this point. So what does that tell you? It converges absolutely in this interval, right? It converges in this interval. If I pick some point x here, then it converges between negative x and x, right? Absolutely, it converges absolutely. If I choose another point here, x, it converges absolutely between that negative x and x, right? So what you see is that if it converges on negative RR, it actually converges absolutely on negative RR. Right? You guys see that? No? Okay, I'll say it again. Okay. So, what I want to say is that if this thing converges on negative RR, it converges absolutely. So remark, it converges absolutely on negative RR. Okay. And the reason is, if I choose any point in negative RR, okay, let's choose some point in negative RR. But here it is, x naught. Okay. Well, my series converges on negative RR, so I know it converges at this guy here. But if it converges at this guy here, then it converges absolutely, right, on this full interval, like this, which contains that x naught. So we have convergence at x naught. Make sense? Right? Does everybody see that? Right? No matter what point I choose here, I choose some point over here. Okay. I choose some point over here. Well, I know we converge absolutely over here, so that means I know we converge here, so that means we converge absolutely at this x. Right? Right. Is that clear to everybody? Anybody have questions about that? Anybody confused by that? I'll say it one more time. I can't really say it any other way. I'm just going to say it again. I'm sorry. But we're trying to see that it converges absolutely at for any point in this interval. Well, choose a point. Here it is. Okay. Well, now choose a point that's a little bit between that guy and the boundary. Right. Choose this other point, P. Okay. Since we converge at P, we converge absolutely for all points between here and here. Well, that includes the x naught. Right? So we converge absolutely at that x naught. So whatever x naught I choose, we converge absolutely there. Okay, so that just follows from the lemma. It's a consequence of the lemma. Okay. So, what we're going to do something with that statement, and that is show you how to find the radius of convergence. Radius of convergence. Okay, so what do I mean by the radius of convergence? What do I mean by the radius of convergence? At this point, we know that the domain of convergence is either, right, it's either a point or the whole line, or it's some interval centered at that point. Right? So if it's just a point, then we say that the radius of convergence is 0. Right? If it's the whole line, we say the radius of convergence is infinite. If it's an interval like this, then we call this thing the radius of convergence. Okay, does that make sense? In higher dimensions, this is actually really a radius. In 2 dimensions, it becomes a disk, and it becomes the radius of a disk. That's why it's called the radius. Doesn't look like a radius, but it actually is one secretly. Okay. So that's what we mean by the radius of convergence. Okay, and so one thing that we need to figure out is what is the radius of convergence? Somebody gives you a power series, and you think you have to figure out what the radius of convergence is. Okay. So I'll just give a bunch of examples. Okay, so here's an example. Summation of -1 to the n, x to the n over n, as n goes from 0 to infinity. Okay. Okay. So okay, so the way you want to think is like this. You know that if it converges on -RR, it converges absolutely there. You know it converges on -RR, it converges absolutely there. That's what we just said over here. Right? That's what we just said over here. Right? So, let's apply rate or ratio test to the sum of the absolute values. Okay. Let's apply the root or ratio test to the sum of the absolute values of that sequence, of that series. Okay. Because if it converges on a rate, if it converges on an interval, this guy is going to converge on that same interval. Right? So let's just find out what interval this guy converges on. Okay? Let's find out what -R this converges on. So let's use the ratio test. Let's use the ratio test. Take the limit of absolute value of x to the n plus 1 over n plus 1 divided by the nth term as n goes to infinity. And you see what happens, right? You get, you're going to end up with the absolute value of x, right? Get some cancellation. You have this n over n plus 1, but that's going to go to 1, right? Yes? Everybody see that? Everybody see that? Right, that goes to x, right? So what does the ratio test tell you? It tells you that this is going to converge as long as this thing is what?
Less than 1.
Less than 1, right? As long as this is less than 1, right? So the ratio test says that this thing converges on -1, 1. Right? As long as the absolute value of x is less than 1. Yeah, Mitch?
Why does the absolute value of x have to be less than 1?
Well, remember what the ratio test tells you, right? The ratio test says that if you get some number, and that number is less than 1, then you converge. And if it's greater than 1, then you diverge, right? So the number that we got was this. Okay, so the ratio test actually tells us that on -1, 1, we have convergence, and outside of that, if we look like this, then we converge outside there. Right? It doesn't say anything about the endpoints, what happens at 1 and what happens at -1. Right? For that, we have to get our hands a little bit dirty. But what it does give you is the radius of convergence. Right? We see that the radius of convergence is 1. Okay, everybody see that? Okay. If you're wondering, like, well, what about at 1 and -1? Well, you have to work this out yourself. You say, well, at x equals 1, what happens? We get summation -1 to the n over n. Does that converge? Does that converge? Yes, it does. By the, right, Claire?
By the alternating.
By alternating series, right? Which converges by alternating series. Right? So at 1 we have convergence. At -1, what do we get? We get -1 to the n times -1 to the n over n, as n goes from 0, 1, n goes from 1 to infinity. Right? So we get summation 1 over n. Well, does summation 1 over n converge? No, right? Diverges. Okay. So after doing this extra work here, we see that the true full domain of convergence is this -1, 1. Right? So our real domain of convergence is -1, 1, including 1. Not including that. Okay, so you have to do a little bit of work to check on the endpoints, but all I'm trying to get across right now is how to find the radius of convergence. Everybody all right with? Everybody all right? Okay. So we'll do a few more examples. We'll do a bunch of examples, in fact. Okay. So another example. X to the n over n squared as n goes from 1 to infinity. Why don't you try it? Why don't you try it? Yeah, sure. So consider the sum of the absolute values and apply either root or ratio tests to it. I'll pass back some homework while you're at it. Okay, talk to somebody nearby. Just talk to somebody and tell them what you think.
So for the retest, you would just
Okay, let's talk. What's the domain, or what's the radius? Anybody want to tell me about the radius? What's the radius? Sam? No? You have no idea? Anybody have an idea? Hannah? It's 1. Yeah, it's 1. Right, so you take this guy, you take the, look at this, the absolute values, right? And then you take the ratio test, you apply it to this guy, right? You get n plus 1 squared divided by x, absolute value next to the n over it, and squared, and just infinity, right? Okay. So that's just applying the ratio test, right? That should be easy, right? And so you end up with, again, the absolute value of x, right? Because you've got this n squared over n plus 1 quantity squared. That's going to go to 1, right? And you've got these things, you've got some cancellation. That's just the absolute value of x, right? And so you see that this converges. So this thing converges if the absolute value of x is less than 1. Enough.
It's okay if I do the limit of absolute root of thing as the book does.
Absolute what?
Limit of the absolute sign and then have this, do the same thing, ratio test.
Yeah, sure, that's the same thing. Right. Do you mean like the absolute value of this? Yeah, that's
And
the same.
without putting x in the absolute value.
That's okay. It's the same thing, right? Because these are positive. N squared, n plus 1 squared, these are positive. Okay, right. And if we cared about the endpoints, we probably should care about the endpoints. Right? What happens at x equals 1? Well, you get summation 1 over n squared, which converges, right? So that's good. What about at x equals negative 1? You get summation negative 1 to the n over n squared. What about that? Does that converge? Sure, right? By what? All that alternating series test, or you could just say it converges absolutely, right? Because negative 1 to the n over n squared, if you take the absolute values, is 1 over n squared. Well, summation 1 over n squared converges by integral test, right? So either way, however you want to think about it, both endpoints are good. So the domain of convergence is this. The radius of convergence is 1. The full domain is, it actually includes both endpoints. Okay. Any questions? Okay. Let's see. Okay, let's do another one. Summation n x to the n over 6 to the n. Okay, let's actually just do this one together. Just for variation, just for variety, let's do the root test on the absolute value. So take the absolute value, take the absolute value, and then let's apply the root test to it. right? So we take the nth root of the nth term, right? So we get n x to the n, 6 to the n. So that goes to infinity. Oops, yeah, okay. That's great. Okay, and you see what happens, right? You get this n to the 1 over n, you get absolute value of x, and you get a 6 on the bottom. And then goes to infinity. Right? What happens to n to the 1 over n? That goes to 1, right? And you end up with absolute value of x over 6. Okay, so what does that tell you? Root test says that number, as long as that number is less than 1, then we're good, right? As long as this is less than 1, we have convergence, right? So in other words, as long as x is smaller than 6 in absolute value, we're good. So our radius is 6. Right. Our radius is 6, and then we need to check the endpoints. So at x equals -6, what do we get? We get summation n times -6 over 6 to the n. In other words, summation -1 to the n times n. N from 0 to infinity. Right? So what happens to that? It diverges, right? Because, why does it diverge? So, because of the divergence test, right? The size of the terms does not go to 0, right? These terms don't go to 0, so it diverges. And that diverges. And at x equals 6, we get the same sort of trouble. We get summation of n from n equals 0 to infinity. Well, that really same reason. Also diverges. Okay, let's just do one more example. So, summation -1 to the n over n squared times 3 to the n times x plus 2 quantity to the n, and from 1 to infinity. Okay. So this is an interval, this is a power series centered at -2. Right? This is a power series centered at -2. So your series, your domain should be centered at that -2. Okay. Take 1 minute and see what you can get using whatever, using either ratio or root test. let me do it because we're starting to run a little bit late on time. So I'm going to apply the root test to the absolute value. So I'm going to look at the I got this x plus 2 to the n. I got n squared. I got 3 to the n. I'm going to raise everything to the n power, 1 over n power. Okay. And you see what's going to happen, right? N over 2, right? We've got this n over 2 divided by n. We've got 3. We've got x plus 2. As n goes to infinity, right? So that's just going to be x plus 2 over 3 in absolute value. Are you okay?
Yeah, we were just wondering where the negative 1 went, but we realized.
I took the absolute value. Yeah. It went where all the other negative ones went. I'm not sure where. Yeah. Okay, so what you see is that as long as x plus 2 is less than 3, right? That is, as long as our distance to negative 2 is less than 3, then we're good. Right? Our radius is 3. Our radius is 3. And then you check the endpoints. It's not all that different. It's going to end up, just to save time, I'm just going to put it down. Both endpoints work. I hope everybody sees how the process. You just use the root test or the ratio test on the absolute values. Okay. So next thing I want to talk about is a theorem about properties of power series. These are kind of interesting. Unfortunately, we're not able to prove them in this course, so I'm just gonna give them to you. Okay. So let's say that you have one function which has a power series expansion, and you have another function that has a different power series expansion. First thing we're going to say is that then the derivative of the first function, has a power series expansion, and the power series expansion is going to be the sum of the derivatives of the terms. So we get n a sub n x to the n minus 1 from n equals 1 to infinity. And the radius of convergence is the same. The radius of convergence doesn't change. Okay. So what this is saying is that if you differentiate a power series, it's okay to switch the power series and the switch the summation and the derivative. Right? But you can change the order. You can change the order. Okay. That's okay if it's finite. That's sort of obviously okay, right? But it's actually true even if this is an infinite series. It's okay. So the derivative of the infinite series is the series of the derivatives, right? It's the sum of the derivatives. The derivative of the infinite sum is this infinite sum of the derivatives. This is called term by term differentiation. Right? So term by term differentiation is okay. not so simple a thing to prove, because we're dealing with an infinite sum. Number two is sort of an analogous thing. If you take the antiderivative of the function, it is the sum of the antiderivatives. It's going to be the infinite sum of the antiderivatives. A sub n x to the n plus 1 over n plus 1 n goes from 0 to infinity. Yes, Hannah?
For the derivative, you said n equal 1 to infinity, but
Yeah.
that makes like,
Well, n equals 0, you don't get anything anyway,
Ah.
right? Because you have 0 times something.
okay.
Okay, and again, the radius doesn't change. And then there's a third thing, that if you take the sum of the power series, then you get sort of what you would expect, just the term by term sum. If you sum the power series, then that thing has a power series where you just sum the terms term by term. Okay, and the radius is the smaller. So this is valid with the smaller radius. Okay, so maybe you've got one big radius and you've got one smaller radius. It's good within the smaller radius. You're not really sure what happens in the big radius. And the fourth one is that if you take a product, then you get, I'm just going to write this, you get multiplication like polynomials. And so you can multiply power series just as if they were polynomials. Okay, so all of this is sort of saying that power series behave like polynomials, right? If you differentiate a polynomial, you just differentiate the sum. Differentiate all the terms, right? If you integrate a polynomial, well, you just integrate all the terms, right? If you add polynomials, you just add the terms. If you multiply them, you multiply the terms. So this is, you could think of this as power series are sort of like polynomials. They behave like polynomials. Okay, so let me give you one example. F of x is summation x to the n over n factorial. Okay. I'm going to just tell you that the radius of convergence is infinite. The radius of convergence is infinite if you run the test on it. What happens if you differentiate this? If you differentiate this, well, you get the sum of the derivatives of the terms. You get the sum of the derivatives of the terms, right? But that's going to be n x to the n minus 1 over n factorial. As n goes from 1 to infinity. Right? Okay. But you see that this n will cancel off with the top n, and we end up with n minus 1 factorial on the bottom. Right? So we end up with summation x to the n minus 1 over n minus 1 factorial from n equals 1 to infinity. same thing as the sum from n equals 0 to infinity of x to the n over n factorial. Right? If n goes from 1 to infinity, I've got x to the n minus 1 over n minus 1 factorial. That's the same thing as x from 0 to infinity, x to the n over n factorial. Right? That's the same thing. Right? Which is the function itself. What function do you know its derivative is itself? E to the x. So, right, so this turns out to be, notice that f at 0 is f at 0 is 1, right? So f is e to the x. I had to check this because it could have been 5e to the x or something like that, right? When you differentiate 5e to the x, you also get 5e to the x, right? So I wanted to check what the value is at 0, right? Since f of 0 is 1, this has to be just e to the x. Okay, we do another example. Okay, summation x to the n over n as n equals 1 to infinity. Okay, if I differentiate this, well, I get summation x to the n minus 1, well, summation x to the n minus 1, so n equals 1 to infinity. You get n, the n's cancel. Right? You get this over n, the n's cancel. Okay. Well, that's the same thing as the sum from x equals 0 to infinity of x to the n. Right? X to the n minus 1 from n equals 1 to infinity, the same thing as x to the n from n equals 0 to infinity. But you know what that is, right? This is 1 over 1 minus x on negative 1, 1. Right? So what does that tell you? That tells you that f prime x is 1 over 1 minus x. If I integrate both sides, I see that f of x is going to be negative natural log of 1 minus x plus a constant. Right? On negative 1. And you can work it out that the constant will be 0 by plugging in 0. Sorry to keep you just a minute over, but let me just do one more. Sorry, last one. So, if I look at 1 over 1 minus negative x squared, okay, right? I know that 1 over 1 minus x is summation x to the n on negative 1, 1. Okay, I'm going to put in negative x squared for my x there. So I get summation negative x squared to the n equals 0 to infinity. 1 over 1 plus x squared. So I'm just plugging into the geometric series. Okay. But if I integrate both sides then, right, is the integral of -1 to the n, x to the 2n from n equals 0 to infinity. Right? What is this? Anybody remember this one? The integral of 1 over x, 1 plus x.
Arctangent.
Arctangent. Right. So this turns out to be arctangent. And from this thing we get a formula for the power series of an arctangent. And we get summation -1 to the n x to the 2n plus 1 over 2n plus 1 plus a constant. And the constant turns out to be 0. So the moral is that these properties of power series allow you to get power series for various functions in this sort of contrived way. It's not. This isn't very good. This isn't a very good way, but you can use these properties to get these sorts of factors. Okay, that's it for today. So, thank you very much.